So this electrochemistry questions. The first question. Now all of these are mostly the latest past paper questions. Uh, so these are the type of questions. Like older questions had a slightly very different pattern, and they were all repetitive. But now the newer questions are more trickier, and they are always asked in a different manner. So the question is: the overall reaction for photosynthesis is shown. And they're saying that what is oxidized in the process according to the following half equation. Use the equation to deduce the half equation for the reduction of carbon dioxide in this process. So this is what is happening now. Electrolysis. What does he mean by the half equation? TK is talking about a half equation for the reduction of carbon dioxide. What he actually means is that in electrolysis, what is this equation? There's an equation for oxidation. So we have that. And let me write that down. You always have two reactions going on. Okay, right in the beginning, we studied this that the number of electrons lost and gained they must be equal. So there's this reaction that's happening, and this is your oxidation reaction. Okay, that's one side. That's the substance losing electrons, and simultaneously there's going to be a reduction equation where a substance would be gaining electrons, but we don't know what that reduction equation is. But what we do know is that both of these equations they add up. So both of these equations they usually add up, oxidation and reduction, if the number of electrons gained and lost are equal, and you get the overall reaction. So you get an overall reaction, and we have that overall reaction. They've already given us the overall reaction that's taking place. So I'm going to write this overall reaction. Now listen very carefully. This is slightly tricky. So it's 6 carbon dioxide molecules plus 6 water molecules, and they're forming C6H12O6 plus 6O2. Now think of this as a math problem. That two equations, oxidation and reduction, they're going to get added up to form this overall reaction. We have been doing this, and I can show you when we were doing electrochemical cells, when we were trying to figure out the overall reaction, like any place over here. Not this, this is electrolysis. Before this, when we were predicting redox reactions, uh, maybe this one. So how did you make the overall reaction? The way you made overall reactions was that there was an equation which had the lowest E naught, which was losing electrons, and there was an equation which had the highest E naught, and which was gaining electrons. So you had an oxidation equation. This is the oxidation reaction where the substance is losing electrons, and there's highest E naught gains electrons. So that's your reduction equation. It's moving in the forward direction where a substance. So you had two half equations, and then you made an overall equation by adding the reactants and the products of the both equations. And the first thing that you did was that you made the number of electrons gained and lost equal. So you multiplied both equations by some number so that the number of electrons gained and lost were equal. Over here, Sn is losing 6 electrons, and over here, uh, chromium, Cr2O7 is gaining 6 electrons. So the electrons gained and lost they must be equal. As anyways, so you added the reactants 3SN2 plus Cr2O7 2 minus are the reactants over here. So these are your reactants, and you added up all the products, and you got this. Now you have to do the same thing, except that the overall equation is already given. One of the equations for oxidation, I think, is given, and you have to find the reduction equation. So it's exactly like a math problem. Now you have to figure out that these are your reactants. What other reactant has to be added so you get, and let me change the color of the marker. What other things need to be added so you get this? So the first equation has two water molecules. Uh, so the first equation has two water molecules, and the products are, I mean, it's forming oxygen, right? Now in your overall equation, one thing that you should notice is that there are 6 oxygens in the product. And there's 6 oxygens that are being formed in the products. So I think I need to multiply this equation by 6 because my product should have, and because my overall reaction has 6 oxygens, so one of my equations should have 6 O2. So I'm going to multiply this by 6. This would give me 12 H2Os. And over here, I'm going to have multiply this by 6. This would be 24. Multiply this by 6, I get 24H plus 1. And this would be, multiply this by 6 would give me 24 electrons. So that's the first thing, because my product over here, the overall equation has 6 oxygens. Okay. Sarah, is this clear? Akib, is this clear?
Yes.
Yes, sir.
Achha, so now the next part, now the missing things. There's, in my overall equation, I'm getting carbon dioxide, which means that in this other reaction, there must have been carbon dioxide. I mean, that's why, because if you add up the reactants, if I make a line over here, you have 2 reactions. One is oxidation, the other one is reduction. So you add up the reactants, there has to be carbon dioxide over here. So 6 carbon dioxides, 12 water molecules from the first one, but over here you have 6 water molecules. That means there must be, over here, there must be, I mean, you must be subtracting 6 water molecules. I mean, that's why in your reactants, you're getting 6 water molecules, because we figured out that the oxygen should be 6. So we made this equation, we multiplied this equation by 6, but we got 12 water molecules in our reactants. So that indicates that 6 water molecules probably got subtracted in this other reduction equation. The other thing is that 24 electrons are being produced. So that means over here, 24 electrons, they must be, because in your overall equation, you're not getting any electrons. So what I can say is, instead of writing it over here, what I can say is that 24 electrons are probably getting subtracted over here. Then I have a glucose molecule over here. So that means in this other equation, there must be, in the products, there must be a glucose molecule. It should be C6. I mean, there must be, in the products, there has to be a glucose molecule. Otherwise, I mean, that's where you're getting this glucose molecule in the overall reaction. Then there are 24 H plus 1 ions. So that indicates, I mean, in my products, there is no H plus 1. So that means 24 H plus 1 probably got cancelled over here. Right? So I'm trying to find this missing equation. Like if you add up the products, you should get this. If you add up the reactants, you should get this. So 6 CO2s plus 12 H2Os and minus 6 water molecules should give you this. 6 O2, that's 6 O2 plus 24 H plus 1 plus 24 electrons. So at the bottom, there's no 24 H plus 1 over here. There's no 24 electrons over here. So over here, it should be minus 24 H plus 1 and minus 24 electrons. Plus there's a glucose molecule over here. So the second reaction should have a glucose molecule as well. So my final equation is this one. This should be this other equation, which should, because if you add this equation to the first one, you get this reaction. Mehfooz, is this clear? Akib, Sarah?
Yes, sir.
Achha, but this equation over here, in an equation, you don't actually have minus sign. So this equation has to be written and it has to be rearranged. You have 6 carbon dioxides. So that's, I mean, you never write minus in a chemical equation. So how do you get rid of the minus sign? Like a math equation, this minus 6H2O, if you take it to the other side, that would be plus 6H2O. So anyway, 6 CO2, I mean, there's minus 24H plus 1. Get this minus 24H plus 1 to the other side. So that's going to be plus 24H plus 1 on the left side. And then there's minus 24 electrons. Take it to the other side. So it's going to be plus 24 electrons. And in my products, I'm going to get this glucose, C6H12O6. And bring this minus 6H2O to the other side so that it becomes plus 6H2O. Okay, so your chemical equations, they shouldn't have minus signs in them. So this is my reduction equation. This is the other equation that was added to the oxidation equation to give you this final equation. So it's 6 CO2 plus 24 H plus 1 plus 24 electrons gives you glucose plus 6 water molecules. Okay? Is this clear? Akib, Sara, is this clear?
Yes, sir.
So now,
Yes, sir.
so if you have any questions, you can ask them. The next part is draw a fully labeled diagram of the apparatus that should be used to measure the standard electrode potential E naught of the oxygen in half equation 1, this one. Okay, so he's talking about this one. So he's asking, how would you measure the standard electrode potential E naught of this equation and include all necessary chemicals? So it's this reaction that we are talking about. Now, the reaction involves a gas. So that means we learned early on how to make electrodes involving gases. So you're going to have a gas jar, and the gas jar is going to have oxygen gas coming in. And the oxygen gas, because remember he's using the word standard, so it must be at 1 atmosphere pressure, so label it properly. And there's oxygen gas and there's H plus 1 ions and there's water. The H plus 1 ions and water, they would probably be in the solution. So you don't have to write water explicitly. You can only, what you can write is that this is H plus 1, aqueous. Aqueous indicates that it is water. And the concentration must be 1 mole per decimeter cube. For a standard solution, the concentration has to be 1 mole per decimeter cube. So these are all the ingredients for half equation 1. Oxygen gas, H plus 1 ions in the solution, and there's water, obviously, because H plus 1 is aqueous. And you would need a platinum electrode. The purpose of the platinum electrode is that if anyone wants to gain electrons or wants to lose electron, they can do it on the platinum electrode. So if somebody needs electrons, they can come to the platinum electrode and gain those electrons, because platinum is a metal and metals have delocalized electrons. So they can gain those electrons over there. Or if they want to lose electrons, then they can do the same and they can give platinum, and the platinum electrode would become negatively charged, or it's going to have lower potential. Is this diagram clear? Sarah, Akib, is this clear?
Yes, sir.
Achha, but this diagram is not complete because every electrode potential has to be measured with respect to a reference point. And I have told you that the reference electrode is your standard. It's always your standard. So it's your standard hydrogen electrode, which has, I mean, there's going to be H plus 1 aqueous in the solution. And the concentration is going to be 1 mole per decimeter cube. And this is taken as your 0 volts. This other electrode, we can look in the data booklet, 2 water molecules, oxygen and H plus 1 plus 4 electrons. We can have a look in the data booklet, and and there's going to be this other electrode. I think it was water and oxygen in equilibrium. So I think it was this one. Water molecules, oxygen and H plus 1. This is 1.23 volts. Let me just confirm. Water molecules, oxygen and H plus 1. So oxygen and H plus 1 are gaining electrons. So it is this electrode. Yes. So it's 1 point. So this one is 1 point. This side would be 1.23 volts. And your E naught cell in this case would be, you'll be getting a value of 1.23 volts. And there's one thing missing, which is a salt bridge. So a salt bridge is always needed to complete the circuit. Plus, this hydrogen gas should be at 1 atmosphere pressure. So that's how you're going to. That's how you make these electrodes. TK will be asked to make diagrams of these electrodes. Moving to the next part, which is for the cell drawn using the data, calculate the E0 cell and deduce which is the positive electrode. We've already done that. It's 1.23 volts. And which one is the positive electrode? Positive electrode, the higher potential is the positive electrode. I mean, this side is 0 volts, according to the data booklet, and this side is 1.23 volts. So it's definitely this side, the left side electrode is your positive electrode. ठीक है? Is this clear? Sara, Akib, is this clear?
Yes, sir.
So the next question is the half equation for the reduction of iodate ions is given. They've given you use the data from the data booklet to predict whether the reaction is feasible when aqueous solutions of iodate ions and bromide ions are mixed. So here's this reaction, and he wants to find out the reaction with bromide ions. So what can bromide ions do? The first thing is go to the data booklet and find out what bromide ions are capable of. Find what bromide ions can do. So if you look over here, you will notice that there is bromide. There's only one equation, which is this one. Br2 plus 2 electrons to Br minus 1, and the value is 1.07 volts. So I'm going to write this equation, Br2 plus 2 electrons, and it's in equilibrium and it's forming 2Br minus 1, and this is the E0 is 1.07 volts. So what's the rule? The higher potential is the one that gains electrons, the lower potential is the one that loses electrons. This is the higher potential, so it would go in the forward direction. It would gain electrons. So this is your high E0. You can remember in electrochemistry, high E0, they always gain electrons. And this one is your low E0. So it's going to lose electrons and go in the backward direction. So your overall reaction is going to be, what you need to do is you need to make the number of, because they've asked, they've actually, I don't know if they've asked to make the equation. Use the data to predict whether the reaction is feasible when aqueous. So they're just asking whether the reaction is feasible or not. But we can actually construct the overall reaction. Okay, although that is not required in this question, but we can do that just for practice. So the first thing is you make the number of electrons gained and lost equal. So you need to multiply this first equation by 2. So this would be 2. This would become 12. This would become 10 electrons. Multiplying by 2, this would become 1. And this would become 6. And multiply this other equation by 5. So this would become 5Br2. This would become 10 electrons. And this would become 10 as well. Now your number of electrons that are being gained and the number of electrons that are being produced, they're equal. And then you can add up the two reactions. You can add up the reactants, and at the same time you can add up the products. So if you do that, the reactants in the first one are these. So that's 2iO3 minus 1 plus 12H plus 1. The electrons are going to get cancelled out, so we don't write them. The electrons lost and gained are equal. The reactant in the second one is 10Br minus 1. And the products. The products in the first one are, these are my products. In the second one, the products are these. So I'm going to add up the products. It's going to be I2 plus 6 water molecules plus in the second one, the product is 5Br2. So this is my reaction, and the E0 cell for the reaction is higher potential minus the lower potential. So it's 1.19 volts minus 1.07 volts, and that gives me 0.12 volts, which is definitely greater than zero. That means, so what in this answer, what you just had to write, you didn't actually have to write this. I mean, this is just for practice. You just had to state that the E naught cell is coming out to be greater than zero, which means that the reaction
Infeasible.
is feasible. Okay, this was the 1 mark answer. So that's the rest of the thing we did all for practice. So it is feasible. So E naught cell, whenever it's greater than zero, that simply means that the higher potential is the one that's going to gain electrons, and the lower potential is the one that's going to lose electrons. And electrons are going to flow between the two electrodes. Now, this is not going to be very feasible because 0.12 volts is a very small value. So electrons would flow between the two electrodes, but very, very slowly. The greater the potential difference, the more quickly the electrons are going to flow. Now, next one is aluminium is extracted from aluminium oxide by electrolysis, and aluminium oxide is dissolved in the half equation for the reaction at the anode is given. Use this half equation to write the ionic equation for the electrolysis of aluminium oxide. So this is again, this is the oxidation equation. Electrons are being produced or lost. So this is your oxidation equation. Now he's clearly saying that aluminium is being extracted from aluminium oxide. So the other equation would be the reduction equation. It would be aluminium ions gaining 3 electrons to form aluminium. This is going to be your reduction equation. This you have to come up on your own. It's pretty obvious that you're making aluminium from aluminium oxide, so it has aluminium plus 3. It changes to aluminium, so that means it's gaining 3 electrons. The number of electrons gained and lost, they must be equal. So multiply both equations by a number so that they become equal. So the first one would be multiplied by 3. And if I multiplied by 3, this would become 6 electrons. The second one would be multiplied by 2. So this would become 6 electrons. And you add up the reactants and the products. So the reactants are 3O2 minus plus 3 carbons, plus the reactants in the other one is 2 aluminium plus 3. And the products in the first one are 3CO. And in the second one, the products are 2 aluminiums. So that's your overall reaction. Now, one thing that we did not do when we were doing electrochemistry, and that is, I say clear this one, last one. Sarah?
Yeah, sir.
Asha, one thing that we did not do, we did electrolysis. One thing that we did not do was were calculations, moles calculation. So remember a few formulas. Okay, this is related to moles calculation. One is Q is equal to IT. This is the physics formula, which is current is going to be in amperes. And time is going to be in seconds. If you multiply current with time, you get charge in coulombs. So you get time in you get the charge in coulombs. So that's one formula that you have to remember. The other one is that one electron, again physics, one electron has a charge of 1.6 times 10 per minus 19 coulombs. Actually, it has a negative charge. Um, but since we are dealing with electrons, I mean, we'll just call it 1.6 times 10 per minus 19 coulombs. So what would be the charge on 1 mole of electrons? Like if you have 1 mole of electrons, that means how much is 1 mole? That means I have 6.02 times 10 power 23 electrons. Okay, that's a huge quantity of electrons. And each electron has a charge of 1.6 times 10 power minus 19 coulombs. So what you get is, from this calculation, what you're going to get is that 1 mole of electrons, if you do the calculation and do the math, 1 mole of electrons, they have a charge of 96,500 coulombs. That is what you're going to get. That one mole of electrons are going to have a charge of 96,500 coulomb. And this is known as your Faraday constant. So Faraday constant is simply, so it is simply the charge on 1 mole of electrons. And the formula is known as F is equal to LE, where L is the Avogadro's constant, or number, and E is 1.6 times 10 power minus 19 coulombs. Okay, we've actually this is actually F is equal to LE. I mean, this one over here. How do you find the charge on 1 mole of electrons? You multiply the Avogadro's number by by the charge on 1 electron. So this is Faraday constant, and that's the formula of Faraday constant. So what's the purpose of Faraday constant? Faraday constant is that it relates charge with moles of electrons. So you can actually, if you know the charge that's passing through the circuit, you can, using ratios, you can find the moles of electrons. So this is the only thing that you have to remember. Like if you have 2 moles of electrons, you should know that the charge is going to be double. So any amount of charge, you can convert that into the moles of electrons that are passing through the circuit. Okay. Aisha, clear है सारा? आके business clear?
Yes, sir.
Yes, sir.
Achha, so just two things, Q is equal to IT and this thing. And this should be sufficient to actually do any moles calculations. So they're saying aluminum oxide is electrolyzed for 3 hours. So the time is given and the current is given. So if time and current are given, you can use Q is equal to IT to find out the charge that's flowing through the circuit. So it would be 3.5. The current is 3.5 times 10 power 5 amperes multiplied by 3 hours. Each hour has 60 minutes and each minute has 60 seconds. So you can try and do the calculation. So if I try and do this calculation, it's going to come out to be 3.5, 10 power 5, and then into 3, then into 60, and into 60 again. So I'm getting a huge number. It's I think 3.78. Akib, did you need 10 power minus 9?
Yes, yeah, 3.78. 10 power minus 9.
Not minus 9. It's 9. 1, 2, 3. Yeah, 10 power 9. Positive 9. Right?
Yeah, positive.
So positive 9. Achha, but that's the charge. That's the coulombs. What can you do with coulombs? You can apply Faraday constant. You can use ratios. You know that 1 mole of electron has how much charge? It has 96,500 coulombs. That's the charge on 1 mole of electrons. So how many moles of electrons do you have that are passing through your circuit, through the carbon electrodes? So your charge is 3.78 times 10 power 9. And using this, you can find the moles of electrons. So just use ratios. So it's going to be this number 3.78 times 10 power 9, I think, divided by. So it's going to be divided by 96,500. And if I do that, the moles come out to be 39,171 moles of electrons. So that's the quantity of electrons that are passing through the circuit. And calculate the mass of aluminium. So how many electrons do you need to make aluminium? We wrote down that aluminium ions need 3 electrons to form aluminium. So it's 3:1. 3 electrons are needed to make 1 aluminium. How many moles of electrons do you have? You have 39171 moles. So how many moles of aluminium would be produced? So it's 3:1. So it's going to be 39171 divided by 3, and that gives you 13,057 moles. Akib, is this clear? Sarah, is this clear? Aisha?
Yes, sir.
Yes, sir.
Yes, sir.
So you're getting 13,057 moles. And if you now he's asking for mass. So once you have moles, you multiply by the MR or AR in this case, which is 27. So you're going to get mass. So we can do that. It's going to be into 27. That gives me 352. So that gives me 352 and 539. That's the mass that I'm getting. I'm going to check this answer. Wait a second. The paper is, it's May June 9720. So let me quickly, so it's 9701 underscore, which paper was it? It was M20 QP42. So 42 MS and M20. So let me quickly check. We did a lot of calculations. Let me just check if we made some silly mistakes. So 352539, and this is, I think, question number 2. So here's the marking scheme. Okay, so we're getting 3.53 times 10 power 5, which is, I think, correct. This is 3.53 times 10 power 5. One thing wrong about this answer is, okay, we're getting the right answer. One thing that's wrong about this answer is, be very careful about this, and that is always check the significant figures of your calculations, which we didn't do in this case. Like over here, if you look at the number of hours, the accuracy of your hours is up to 2 significant figures. He gets 3.0 hours. So he's sure about this first decimal place, but not sure about the next one. And the current is also accurate up to the second significant figure. He doesn't know whether it's 3.51. Digits after that are missing. So it could be 3.51, it could be 3.501. So the accuracy beyond that is missing. So your current is accurate up to 2 significant figures. Now, if the values that you're inputting, they are accurate up to 2 significant figures, your answer cannot exceed or have an accuracy more than 2 significant figures. So you're going to round this off to 3.5 times 10 power 5, or you can round this off to 350000. TK, make sure you do this, and that's what they have done as well. If you look over here, they've actually accepted the third significant figure, but the answer is going to be accurate. It can't be more accurate than the values that you're using to get this answer. Okay, Sarah, is this clear? Aisha, Akib?
Sir, the aluminium,
Yeah.
13,000 from where we got?
These
13,057, yes.
you get this right. We got the moles of electrons, right?
Yes.
So 3 electrons produce 1 aluminium, right? So it's
Yes.
3:1. So every 3 electrons they produce 1 aluminium. So 3917 moles. Divide that by 3, you get this number. Is this clear?
Oh, okay, thank you. Yes.
As the next one, I said always remember this significant figure part. Okay? If you had written this, you would have lost 1 mark at least, depending on the examiner's mood. So remember this significant figures. How many significant figures you should use? As the next part is cryolite can be made from SiF4. You just have to write an equation for this reaction. They've actually written everything down. Let me just quickly check. Cryolite, the first step in the conversion is the reaction of SiF4 with water. And what does it produce? It produces H2, SiF6, and SiO2. Now, one thing you notice is that this is probably not a redox reaction, because if you look at the oxidation state of silicon over here, it is +4 because fluorine is -1. And if you look at the oxidation state of silicon over here, we can find that out. 2 hydrogens, that's +1 into 2. Plus there's 1 silicon, that's X. And then fluorine is -1 times 6. And the whole molecule has a charge of 0. So if we solve this, X comes out to be +4 again. So this is definitely not a redox reaction. The reason I wanted was I was actually checking whether it's a redox reaction is that when you balance a redox reaction, you have to balance the number of electrons gained and lost. Okay. So in this case, that was the first thing that we did. If we go back, right in the beginning, we did this, that whenever you have a redox equation, you balance the number of electrons that are being gained and that are being lost. They have to be made equal. So always check when you're writing equations whether it's a redox reaction or not, because that's an additional thing that has to be done. So this equation is kind of easy because you just have to balance this equation. So there's 6 fluorines and there are 4 fluorines. So you'll just balance this equation because it's not a redox equation. You should balance this in the old-fashioned way. I can make fluorines 12 by multiplying this by 2 and this by 3. So silicons would be 3, which is 3 over here. I mean, the 2 silicons over here and the 1 over here. So that's balanced. And then I can balance the number of oxygens. They're 2. So the equation is balanced. Okay. So just remember, when they're trying to make an equation and asking you to write an equation, make sure that it's not a redox equation. Because if it's a redox equation, you have to do a lot of other things as well. This part is gold is an unreactive metal that can only be oxidized under define the term standard electrode potential. So it is the potential difference calculated between a standard electrode and a standard hydrogen electrode. Okay, that is exactly what we did over here in the first question where we I think drew electrodes. Electrode potential between a standard electrode and a standard hydrogen electrode. So okay, we'll continue with this in the next class then, okay? So if you have any questions, you can ask me.
Can I get these questions? Like,
yeah, I'm going to send them in the WhatsApp group, okay?
Right. Thank you.
Okay, take care.